What's up, guys? Mr. Cully here, and today I want to just go over some of the lessons that we were doing on polarity. And this stuff is a little bit complicated, abstract, so I just thought it'd be useful if I put together a resource video for you guys to look back at whenever you'd want. So I apologize, don't sound great today, but we're gonna get through this video anyway. So let's go ahead and take a trip back to the beginning when we talked about polarity and showed you this picture. And the reason is because I think this picture is a great representation of actually what's going on chemically. Now, before I dive into that, let's first remember what covalent bonding is. And covalent bonding is the sharing of electrons. Sharing of electrons. And that's what we learned covalent bonding to be. Ionic bonding is transferring, covalent is sharing. And so, in the case of sharing, sharing is usually assumed to be done equally, but that's realistically not the case. Sharing is almost never equal. In fact, sharing, especially if you have siblings, you would know that sharing is not equal most of the time. And so, in the case of let's look at this picture. In the case of tug of war, you got these two dogs that are sharing the same rope, the same toy. They're tugging on it, but usually, what happens in tug of war is someone wins. Someone's stronger than the other. And that's the case with sharing electrons as well, is that usually there's an element that pulls on the electrons more than the other. So let's take a look at a case. With water, so let's take a look at water, H2O. So just look at the picture at the bottom of the slide for now. We got H2O. We know that hydrogen each has one valence electron and oxygen has six. Well, they are going to share to complete their octet. So what does that look like? Looks like that. So that's nothing new to us. But what we assumed before was that sharing was equal, and that's not the case here. So oxygen is actually hogging them a little bit tighter than hydrogen is. Okay, what does that create? Well, think about it. Electrons are negative, right? So if I am hogging electrons, what is that going to make me? What charge would that make me? And the answer it would be negative. So between oxygen and hydrogen, we can see right here, these guys right here. If oxygen is hogging these electrons slightly more than hydrogen is, what charge would we expect oxygen to have? And we would expect it to have a slightly negative charge because it's hogging onto these electrons more than hydrogen is. So that would make oxygen slightly negative, and that would make hydrogen slightly positive. So there's this tug of war going on between oxygen and hydrogen. Anywhere you see a bond, anywhere they're sharing electrons, there's a tug of war going on. So the question is, which element is tugging more? Whichever element is tugging more is going to be slightly more negative, and the opposite, whichever one is tugging less, is going to be slightly more positive. Because electrons are negative, if they're hanging around you, you're going to be more negative. It's just the case. So there's this concept that we learned a little while back called electronegativity. And electronegativity is simply how much does an element want to have electrons around it? How much is it going to tug on electrons? How much does it attract electrons? That's all electronegativity means. So we talked about this periodic trend way back when. We saw that electronegativity increases as you go from left to right and from bottom to top. So that makes sense based on this graphic here. So we can see that there's these numbers associated with the elements. What are these numbers? Those are just electronegativity values. Again, what's electronegativity? How strong that tug is towards the electrons. So we're looking at this and we notice that over here in the top right hand corner we got fluorine. Fluorine has a higher number than any other element on this chart. Well, that means fluorine's the most electronegative element. Why is that? Why does fluorine want an electron so bad? Well, it's got 7 valence electrons and it's the smallest. Well, what does the smallest have to do with anything? Well, remember, if it's small, then that means the electron is going to be closer to its nucleus. So the electron that it would get would be closer to its nucleus. So that's important for us to remember. Kind of like how the Earth is, as you get further away from the Earth, the gravity affects you less. Same thing with the sun. As you get further away from the sun, the gravity affects you less. The closer you get, the stronger that pull is. Well, fluorine only has that one full shell. So it's pretty small, and so the electron would actually be pulled in really, really tight to fluorine, as opposed to, you look at astatine down here, that's going to be pretty small. All right, so where are we going to go with this? So these values, right? These values are relative. We only use these in a relative sense. What do I mean by that? Well, if I want to know if there's a bond, let's say, between oxygen and hydrogen. oxygen and hydrogen, and they're sharing electrons. I want to know which one's going to be hogging the electrons more. Well, how would I figure that out? I would look at these values. Well, oxygen's got a value of 3.5 and hydrogen's got a value of 2.1. What does that mean? That means oxygen's got a greater electronegativity. What does that mean? It means it's tugging on those electrons more. What does that mean? It means that oxygen's going to be slightly more negative than hydrogen is. Oxygen will be slightly positive and hydrogen will be slightly negative. So we use these values in a relative sense to see, okay, which one's stronger at pulling in electrons with a bond? And that's going to determine if there's polarity within the molecule. Now, let's say we get two very, very similar atoms. So let's say that sulfur is bonded to carbon over here. They're both 2.5. Well, then what? We would say, okay, there's a very, very close tug with both of them. It's almost equal. It pretty much is equal. So is there going to be anyone who's winning that tug of war battle? And the answer would be no. So therefore, there's no charge distribution. Let's take a very, very wild example. Let's take fluorine, which is 4.0, and cesium down here, which is 0.7. If they were to bond together, what would that look like? Well, fluorine is so much stronger compared to cesium that it's basically going to take those electrons away. So these numbers help us kind of visualize and kind of understand what's going on with the electrons within a bond. So we are going to be taking the difference. So if we get two elements, we're going to take the difference between these values to determine, okay, who's winning the battle more? And what does that matter towards the bond? All right, so let's take a look at what that means. So let's not look at nonpolar and polar for a second. We see that we have covalent bond, and ionic bond, okay? So just to summarize, covalent bond is sharing electrons, ionic is transferring, okay? But what we've learned in freshman year and for a while in this course was that there's only two types of bonds, and that's covalent and ionic. Well, that's not necessarily true. There's actually two types of covalent bonds, and one's called nonpolar and one's polar. So the way that we're actually supposed to look at bonds is more of this spectrum, okay, of where are the electrons, how close are those electrons attracted between two elements. And so, for example, if we wanted to know who's winning the tug of war battle between carbon and hydrogen, what we would do is we would look at the values of carbon and hydrogen, the electronegativity values of carbon and hydrogen. All right. And so we would take those values, so 2.5 and 2.1, and we'd subtract them, the bigger one minus the smaller one. So all I'm doing is I'm getting those values from the periodic table chart right here. So 2.5 and 2.1. So 2.5 minus 2.1 is 0.4. That in a scale of about, let's see, what is the scale range here from 0.7 to 4.0? That's not a big scale, but 0.4 is pretty small. What does that mean? These guys are pretty equal in strength, okay? Yeah, there's like a zero point 0.4 between them, but in general, those are pretty equal. So what we say is if they're pretty equal strength, if they're tugging with the same force, virtually the same strength, then that means that no one's winning that tug of war fight. What does that mean? There's not going to be anyone who has more electrons than the other. Okay, they're essentially just they're pulling with the same amount of force. No one's going to have electrons around them more than the other. So what does that create? It creates a nonpolar covalent bond. Nonpolar just means that there's no distribution in charge. All right. Well, let's say that the tug is a little bit stronger. Let's say like between carbon and oxygen. Well, carbon's 2.5, oxygen's 3.5. The difference between them is a little bit greater than this difference was. What does that mean? Then that means that someone's pretty strong in this fight. So oxygen's actually very, very strong. It's tugging on those electrons very, very strong. So that means that oxygen's going to be actually slightly negative and carbon's going to be slightly positive. So now once we get our value to be between 0.5 and 1.7, that means that we're assuming that there's actually going to be such a greater tug that it's going to be creating a difference in charges. All right, so oxygen is strong enough in this case that it's actually pulling the electrons away. They're not sharing equally, and it's more so going to have a charge to it. This will make sense here in a second. And then let's assume that the bond difference or the electronegativity difference between two elements is so great that it's greater than 1.7. At that point, it's almost like they're not sharing at all, okay? Sodium has such a low electronegativity value that it's not tugging on electrons at all. Chlorine's got a very high electronegativity value. The difference between those is not very great. I'm sorry, is very, very great, which means that it's going to be uh, considered they're not even sharing anymore. It's more so like I'm just giving you the electron. All right, let's look at what this looks like visually. All right, so we got this chart. This chart is actually very, very good. We got covalent bonds, two different ones are polar and nonpolar, and we have our ionic bond. Okay. So let's take a look at what this means. Sharing of electrons. All right. If it's nonpolar, we're saying that the sharing of electrons in the bond is equal. Okay. Remember, polar means like there's going to be someone who's winning, someone who's not. Well, if the sharing's equal, we're saying that it's nonpolar. Okay. If it's polar, someone's winning. If it's nonpolar, someone's not winning. All right. So if we're trying to imagine the electrons between, let's say, a random element A and a random element B, if it's nonpolar, they're going to be sharing these right in the middle. Okay, right in the middle, right down the line, they're tugging at them equally. They're not going anywhere. Think of this as a tug of war battle. Okay, so the sharing of electrons is equal. How does that differ with polar? Well, that means if it's polar, one of these guys are winning. Okay, one of these guys are stronger than the other pretty significantly. So between A and B, you can see here that B actually pulls those electrons closer to it than A does. All right, what does that do? That makes B slightly negative, okay? So I'm going to put slightly negative there, and that makes A slightly positive. So these electrons right here make B slightly negative because they're closer to B. B is stronger in a sense, okay? All right, so that's unequal sharing. They're not sharing equally. B has them around it longer than A does. All right, and so over here with ionic, if B is super strong, then it's almost like A is not getting any part of it at all. It's not sharing anymore. B is just hogging it to the point where it's basically cut off from A. So at that point, it's not even slight charges anymore. Those electrons we're saying are with B, so it's got a full negative charge, and A's got a full positive charge. So there's this gradient. Depending on how strong B is, will tell you, okay, is the sharing equal, unequal, or is it so unequal to the point that we're saying it's transferred over? Okay, and that's going to determine if it's a slight positive charge or a full positive charge, or in this case over here, no charge at all. There's no charge difference at all. So it's kind of like a gradient. However strong B is will determine, compared to A, will determine if it's polar, nonpolar, or ionic. All right. So dipole movement, I'm not gonna talk about this right now. But how do you know? How do you know if it's nonpolar, polar, ionic? Well, the difference between the electronegativities will tell you. If the difference in the electronegativity of A and B is less than 0.5, then it's nonpolar. If the difference is between 0.5 and 1.7, then it's polar. If it's greater than 1.7, then it's ionic. Okay? So we're going to be using that right now. Let me move this out of the way. Okay, so HCl, we're looking at these. HCl, we need to find the electronegativities of both of these elements. We're looking at a bond between H and Cl, hydrogen and chlorine. So hydrogen's got a electronegativity of 2.20. You could find that in your periodic table. Chlorine is 3.16, I believe. I believe that's right. If it's not, we'll just assume it's right. Okay. So we need to find delta En. Well, this triangle En, that just means change in electronegativity. Okay, we want to find the difference in electronegativity of these two numbers. Well, to find the difference of anything, you just subtract it. So it'd be 3.16, the bigger number, minus 2.20. It's always going to be the bigger number minus the smaller number. All right, and what you get here would be 0.96. Okay, that is our difference. That's the difference in the tug of both of these. Chlorine pulls with 3.16, hydrogen pulls with 2.20. What's the difference? 0.96. So what I do is I take this number, and I look at this chart, okay? 0.96, where does 0.96 fall on this chart? Well, 0.96 would be in this category. What is this? This is polar, okay? It's a polar molecule. So this must be a polar bond. Polar. Technically, it's called polar covalent, but it's a polar bond, okay? So the last thing I need to do is I need to draw this. I need to draw this. So I've got my bond down here, and the way I'm going to draw it is I just need to show the charges now. Well, because this is polar covalent, then that means that I'm going to have partial charges, okay? Partial charges, which means one of them is winning more than the other, okay? If it's polar, one is winning. Well, which one is winning? Which one is having a stronger pull on the electrons? Well, if you look back at the numbers, chlorine has a higher electronegativity value, so it's going to be pulling on those electrons tighter, okay? So what charge would that make chlorine have? That would make chlorine have a slightly negative charge if it's pulling on those electrons tightly, which means hydrogen would have a slightly positive charge, okay? So now I just assign my charges. Chlorine is slightly negative, hydrogen is slightly positive. So the last thing I want to do is I'm going to draw something called a dipole. And a dipole is simply an arrow pointing to the most electronegative element, or the most negative element in this case. So what that looks like is I'm going to draw an arrow from hydrogen to chlorine, okay, to chlorine, because it's going to point towards where's the tug going towards. And chlorine is winning this tug of war fight. It's pointing towards chlorine. And the only other thing that we need to add is the tail of this arrow has a plus sign. It kind of looks like a plus sign like this. So it's going to be from left to right. It starts at hydrogen, the most positive side, going towards chlorine, the more negative side. All right, to recap, what do? You write down the electronegativities of each element. Then what? Then you find the difference between those electronegativities, okay? Higher number minus the lower number. Then you get this difference. Then you take that difference and you go to the chart. And you say, okay, is that difference less than 0.5? Is it between 0.5 and 1.7? Or is it greater than 1.7? And then that's going to tell you what kind of bond it is. All right, so in our case, it was a polar bond, which means that the sharing of electrons was unequal, which means that we're going to have partial charges. Okay, one's going to be slightly positive, one's going to be slightly negative. All right, well, how do we figure out which one's going to be slightly positive and slightly negative? Well, in this case, chlorine had a higher number, had a higher electronegativity, which means it's pulling on the electrons more, which means chlorine's going to be slightly negative, and hydrogen's going to be slightly positive, which means the dipole, which is just showing where's the charge head, is moving towards chlorine. There's a tug inward towards chlorine. All right, and that's it. All right, let's do another one. We got carbon and oxygen. All right. I don't know these numbers, so let's take a look back at the table. So carbon's 2.5-ish, oxygen's 3.5-ish. So we got 2.5 and 3.5. All right, delta E, and how do we find that out? Subtract them. Bigger number minus smaller number. So 3.5 minus 2.5 equals 1.0. And, this is not the same as the numbers on your periodic table I gave you. The one I gave you is more specific and more up to date, but we could still do it anyway. So the difference is 1.0. Where does that fall on our chart? Well, 1.0 is between 0.5 and 1.7. So again, this one is polar, which means it's going to have partial charges. So this is polar bond type. This is polar covalent. So between C and O, we're going to have someone that's winning here. Which one is winning? Well, oxygen has the higher value, so oxygen is going to be the one that's winning, which means it's going to be slightly negative, and carbon will be slightly positive. And how would I draw my dipole? Well, the dipole points towards whichever element is winning the battle, whichever one is tugging more. So it's going to look like that, and my positive end will go down there. And that's it. All right. All right, the NC bond. Again, I don't know the numbers, so we're going to go back. So we're looking at nitrogen and we are looking at carbon. So 2.5 and 3.0. 2.5 and 3.0. So I'm actually going to say that carbon is 2.51 and nitrogen is 3.0 just for this example, 3.0. And I'll show you why. But delta En, okay, let's find delta En. So we take the bigger number, which is 3.0 minus the smaller number, which is 2.51. And what do we get? We get 0.49. Okay. So where does that fit in on our chart? Well, 0.49 is less than 0.5. So what does that mean? It means that it's nonpolar. They're basically pulling with relatively the same strength, okay? It's negligible. It's almost like, okay, yeah, maybe one's slightly stronger, but we're saying that they're basically the same strength. So what does that mean? That means that if they're pulling with the same strength on these electrons, then no one's winning. There's going to be no charge to draw, okay? No charge to draw. So in this case, the bond type is non-polar covalent. We're saying that they're basically sharing equally. So if I were to draw the bond, there's no charges to draw because neither of them are winning this battle, essentially. Yeah, okay, maybe a little bit, but if it's below 0.5, we're saying, okay, virtually they're sharing them equally. We don't need to draw any charges. It's pretty even, okay? So anytime you have a nonpolar covalent compound, or bond, I mean, you don't draw any charges, okay? Because we're basically saying that it's even tug of war. Only if it's uneven tug of war, if this difference is greater than 0.5, are we to be drawing charges and dipoles. But for this case, if it's not polar, you don't draw anything. All right. And then I'm not going to go through this problem, but again, here you got two of the exact same element. That's the case of where you know that delta En would be what? It would be 0. Why would it be 0? Because you're taking the electronegativity of oxygen, which I forget what it is. I think it's like 3.5. So it'd be 3.5 minus itself, 3.5, which is 0. Okay? So what kind of bond type would that be? That would be non-polar covalent because they're sharing it very, very equally. And what would the drawing be? There would be no charge distribution. Okay? So anytime you have an element bonded to itself, okay, that's an absolutely equal match. It's going to cancel itself out. You take both of their electronegativity, subtract them, it's going to be 0. Bond type is going to be nonpolar. There's nothing to draw.